Alright, I'm just putting some things up as people filter through. Alright, getting the rules up there so that we have the rules. Them rules, them rules, them rules. That explain how logarithms manipulate. And let's see, we were looking at the logistic equation last time. I want to look at different log models. Sorry, get my notes back up on my little stand here and my other class notes. Yeah, let's look at some models. We're just going to be doing some examples today of different models. Hello, Billy. And I'll keep the rules up here as I get my notes together. Two seconds here. All right. I'm going to take some different models from the textbook and we'll work through them. Let me get over to my blackboard here. But again, these are always a good place to start your thinking from when dealing with logarithms or exponents. It is our magical sauce here. But if I have some base and I take the log of that base towards it, I can pull the exponents down. The other thing is if I have something to a power in a logarithm, I can pull the power out front. And these things will help us manipulate more variables are in the power, and we need to pull the variables down. All right. So I'm going to be looking mainly at examples from section 7, where we construct models. So in general, this is like the application of logistic models. Alright. Let's open up some windows in here. It's very, very warm. Alright. So I think we'll look at number 23, which uses a logistic curve, which I wanted to show. A logistic model. And so we're on page 491 in the book. And so it says, the following table shows the number of cell phone subscriptions in India in billions for the selected year. So we're going to have cell phone usage, that just jiggled about there, sorry about that. Usage in billions for the years from 2005 on. And so what we get is 2005. The usage is 0.05 billion. 2006. The usage is 0.12. And I'll put the rest of the chart up here. I won't scream out each data point. One. So we're going to go all the way up to 2011. So I'll write my other data points here. And their values. And so we have cell phone usage for the number of cell phone youths. Since there's a population here that has a total number, we're going to look at a logistical model. So there's some carrying capacity. An enclosed population or an enclosed environment is a usually good sign that you can use a carrying capacity. And so we need to solve for the variables in the carrying capacity. So we'll say usage from time. Now I'm going to measure time. I'm going to call this year 0. And this year 1, and this year 2, and this year 3, and so on. I'm going to count time from 2005. So we can kind of say, hey, time 0 is at 2005. So if I ever solve for t, if I get an answer of 9 for t, 2005 plus 9 would be in 2014, right? It just makes the number smaller and easier to deal with, to have some starting time. And logistic models are not bad. All right, so let's look at our general logistic equation. We have the carrying capacity of the population. And let's see, your book. Yeah, your book uses the same variables I had. Some books use different variables. I'm just making sure. Are they using a negative bx? Yes. All right, so what we can do is we can solve for a couple different points of data. And we can find these constants by solving for a couple different points of data. All right, so then what we want to do here is look at what this carrying capacity is first. So notice, if I made a small nomenclature error. This is an x, this is t as time goes on. So let me fix that, sorry. Because this is the important part with a carrying capacity model. At time equals 0, we get 1 plus a. Right? Because at time equals 0, this out here becomes 0, because b times 0 is 0, and e to the 0 is 1. So we get 1 plus a. Now, if t were to go towards infinity, t were to keep getting bigger and bigger and bigger and bigger and bigger, our graph of a negative exponential is it gets closer and closer to 0. So as time goes on, this part gets closer and closer to 0, which makes this c over 1. So it approaches some number. But very early on, when b times t is less than 1, this looks like a positive. It has a positive end to it. And so what we need to do is we need to find the b constant and the a constant. Well, at time equals 0, we know our answer is 0.05. So we can take this c, 1 plus a, oops, hit the wrong pen here, but we're getting there. 1 plus a is equal to 0.05. I'll cross multiply. So this becomes c equals 0.05 times 1 plus a. I will distribute 0.05 plus 0.05a is equal to c. All right, so I have 3 unknowns. I'm going to need 3 points in this equation to help me find it. So I'm going to take this. I guess I'll keep this in yellow over here, and I'll find my next 2 in different colors so I can put them all together. I'm going to subtract this from both sides, so I'm going to get negative 0.05a. I'm going to leave a little space, plus c equals 0.05. Taking this equation here, and I have my relationship for 2 of the things I don't know. All right, I'm going to switch over to blue, and I'm going to look at what happens when time equals 6. I want to go to the far end. I'm going to go to this one here. And so I'm going to have c over 1 plus a e to the negative 6b. And I know that's equal to 0.85. Scroll down. So again, I'm going to cross multiply. I'm going to get C is equal to, I'm going to multiply this through as I go, 0.85 plus 0.85 A times e to the negative 6b. So I now have a and b in my equation, and I have c. Notice I have three things. So to figure out what a, b, and c are, I need 3 data points. So I'm going to grab one more, and then I have to put this all together. So let's grab my other one. I think I'll go, let's see, there's 6 of these, so I'll go right in the middle. I'll grab that one. So I'll say u of 3 is equal to c 1 plus e to the negative 3b. And that's 0.14. Or 0.40. Not 14, sorry. Writing things but saying them odd. I hate when I do that. Do that a lot at the blackboard, where I'll be writing it and I say it. It's funny when you analyze your thought process of what you're writing versus what you're saying. Nope, I have my A out front here. My bad. So again, I'm going to cross multiply, and I get 0 equals 0.40 plus 0.40 A e to the negative 3b. All right, so I have 3 equations, and I'm going to write them down in their respective colors down below here. I have this one, and this one. So we're going to bring these together. So equation number 1, C equals 0.05 plus 0.05A. And equation number 2, C equals, where is the other one? 0.85 plus 0.85A e to the negative 6b. And equation number 3, C equals 0.40 plus 0.40 A to the e negative 3b. And so we have these 3 things going together. If we can find A, we know C immediately. So I think my focus is going to be figuring out how I can find B and A. So I can get rid of C in these other 2 equations. So for here, wherever I see C, I'm going to replace it with this. So number 2 becomes 0.05 plus 0.05A equals 0.85 plus 0.85 A e to the negative 6b. And for the third one, 0.40 plus 0.40 A, whoops, I have to replace my C first, sorry about that. I'm replacing C, I went right to the equal sign, with 0.05 plus 0.05 A is equal to 0.40 plus 0.40 A e to the negative 3b. Now there's a general rule of thumb in algebra. For every variable you don't know, you need that many equations. And so I have taken equation 1 and I've plopped it into equations 2 and 3. Notice I have gotten rid of the variable C. If I find A now, I will know what C is. So all my information is contained in these 2 equations. Well, I'm going to clean these up, and I'm going to try to separate A from B and my constants. So the thing I note is I have a constant here and a constant here. and a is in both of these terms. So I'm going to bring the a terms together on the left-hand side. So 0.05a minus 0.85a e to the negative 6b. All right, I've subtracted this from this side. It brings it over to here. That's still sitting there. I'm going to subtract this over. So I'm going to get 0.85 minus 0.05 or 0.80. I subtract this over. And so equation 2 becomes this. Should have done that in blue. Well, I will fix that in a tick. That's nice because we can separate it. So I'm going to continue to work on equation 2. I'm just going to change it back to blue because I was being silly. Now notice both of these have an a in them. So I can pull out an a. 0.05 minus a, whoops, I pulled out the a, e to the negative 6b equals 0.80, or a is equal to 0.80 over 0.05 minus e to the negative 6b. So I manipulated equation 2 so that I have a term for a. Right? I took everything on the I took equation 2. I put all the a's on the left hand side. So I had 0.005a. I subtracted from it 0.85a e to the negative 6b. I put all the constants on one side, so 0.85 minus, and I lost right here because I was rushing, because I was getting towards my point. Right, that's minus 0.85. That's minus 0.85. My apologies. I was rushing to the punchline. Let me get my eraser out and just tidy that up. Hold on 2 seconds. (0.05) minus 0.85 e to the negative 6b. Okay. So I subtracted this from the left-hand side. That gave me this expression. I subtracted this from the right-hand side. That gave me this new constant. I factored a out front because both of these terms had an a, right? That had an a term and that had an a term. And I divided both sides by this. So now I have a on its own. I'm going to do the same thing for I'm not even going to do the same thing for equation 3. I'm going to put this into equation 3. Put this into equation 3. And I'm going to do it in a way, I'm going to do the same rearrangement. And what we're going to want to do is we're going to want to get all of the b's together. All of the b's together. All right, so let's see here. There's equation 3, so I'll go back to green. And so I have 0.05. I'm going to subtract that from each side. And so 0.5a minus 0.40 a e to the negative 3b. All right, subtract that from both sides. And then I'll subtract the 0.05 from both sides, which gives me 0.35. I'll do the same thing. I'll factor out an a. 0.05 minus 0.40 e to the negative 3b equals 0.35. And a over there will equal 0.35 over 0.05 minus 0.40 e to the negative 3b. And so now equation 3 looks like this. And I've isolated A. And I've really got myself in a much better place because I have A, and C isolated in terms of the other variables. And so what I can do here is I can say this A has to be equal to this A. And so I'm going to blend these two equations together so they're going to turn purpley. If I say this, 0.80 divided by 0.05 minus 0.85 e to the negative 6b is equal 0.35 over 0.05 minus 0.40 e to the negative 3b. And look what I've done. I only have one variable, it's b. I have gotten rid of multiple variable dependencies. I can solve b. Once I have b, I can come back here and find a. Once I have a, I can go back up to equation 1 and find c. So we will cross multiply. So I'm going to 0.8 times, so I'm going to cross multiplying these ways. So 0.8 times 0.05 minus 0.40 e to the negative 3b is equal to 0.35 times 0.05 minus 0.85 e to the negative 6b. Negative 6b. Right on the edge of my board there. Alright, I'm going to propagate this number through. This is where your calculators are your friends. I did have a calculator that was my enemy once. I called him Robert. He beat me over the head with numbers. He tended to do it when I was asleep. So this multiplication becomes 0.04 minus 0.32 e to the negative 3b. And then this one becomes 0.0175 minus 0.2975 e to the negative 6b. All right, I'm going to get the terms that have e together. And I'm going to do that by adding this to both sides. So I get 0.2975. It's going to be positive coming over here. E to the negative 6b minus 0.32 e to the negative 3b. And I'm going to bring the constants together. I'm going to have this minus this. And this is a negative 0.0225. I'm getting closer. I've got my B up there, right? My B is separated, and I need to kind of find a way of getting my B all on its own. Which means we're going to have to dive into our rules of exponents and logarithms. So, all right, 0.975 e to the negative b to the 6th power minus 0.32 e to the b to the 3rd power plus 0.0225 equals 0. Notice these powers go down by 2. Just like these powers go by 2. So I can, with a little wizardry, make this a quadratic function. I can say e to the negative 2b, or 3b, squared minus 0.32 e to the negative 3b plus 0.225 equals 0. That's my quadratic form. Make my b's look like b's, sorry. So I can make a quadratic equation out of it if I say u is equal to e to the negative 3b. That becomes 0.2975 u squared minus 0.32 u plus 0.225 equals 0. I don't know if I said it well enough, and I was hinting at it, I was laughing at it. Is logistic equations, are, if you haven't noticed, are using everything we did. Which is kind of why it was meant to be my last example. It walks us through the culmination of everything we did. Alright. So, we'll use our quadratic equation. We'll say that u is equal to 0.32 plus or minus the square root of 0.32 squared minus 4 times 0.225 times 0.2975. All over 2 times 0.2975. I tell you, this is when your calculator is your friend. Minus 5. Negative number. And I have a sign error in here, because I did this earlier last night. So where did I add instead of subtracting? Cross multiply, 0 point negative 3.2 over there. That's a negative 0.45, that's right. Now I gotta go back through last night's notes. I'm just off by a negative sign. Usually it's when I do this part here that I mess up my negative signs. Let's see, I brought that over. Brought that back over. I think that's the negative. I think my negative is on this thing hanging out on the end. Go back through 0.279, 0.075. This is where I wish I had a blackboard. I could look over it all. Because when you make a small sign error. I forgot the 0. Ah, thank you. let's see, 0.0. I forgot a leading zero on one of the terms. Ah, right there. I lost the zero there. Thank you, Billy. I knew. Shouldn't have been getting a negative number. Thank you. Good eyes. And it wasn't too far up. Let me try that again. Billy has the best eyes for my Scrivener errors. Yes, that's much better. The thing in the square root becomes 0.075625 plus or minus 0.32 all over 2 times 0.2975. I'll do the addition one first. I like calculators. I remember when we used to do these things by hand and we were only allowed one problem in an exam period. So the addition, I get 1 for my first term. Oh wait, I forgot to, yeah. 0.32 plus the square root of 0.75625 is 0.595. Divide by 595 and you get 1. So that's a pretty neat way of getting a 1. But you will see the 1 gets thrown away. We change this to a minus. And my other term is 0.075630252. I'll keep extra decimal places for right now. So these are our two possibilities. But remember, this was u equals e to the negative 3b. So I get 1 equals e to the negative 3b. And I get, I'll just put my equals e to the negative 3b here. So to find out what b is, I take the natural log of both sides. So ln of 1 equals the ln of e to the negative 3b. So negative 3b, well, what is the natural log of 1? It's 0. And so this gives me a b equals 0. And if b equals 0 in my logistical model, then we're in what's called the steady state, where the carrying capacity is the only thing driving. So we'll ignore this one because it doesn't do anything for us. But this one here, I'm going to take the natural log of this, 0.07563. Let me get my numbers right here. 7563025 is equal to, when I take the natural log of this, I get negative 3b. So b is equal to the natural log of this large number here, well, very small number actually, divided by negative 3. Which is approximately 0.861. 0.861. And so now that's our B value. So I'm going to come up here and I want to find A. So I'm going to take this one right here and find A. So we're going to say A is equal to 0.80. Come back down here. Turn back to bright blue for this. A is equal to 0.80 divided by, lots of scrolling, 0.05, 0.05 minus 0.85 e to the negative 6 b. Make sure I have the numbers right. Yep. But we already know what b is, so we fight with our calculator a little bit and we plug it in. See, the thing about systems of equations is once you get the one chunk, the other chunks fall in a lot quicker. It's almost that work to get b is so hard that I always find this kind of this part here of typing all this in the calculator to be a letdown. Thanks for finding that zero, Billy, because I don't think I would have seen that right away. I was looking for a sign error because that's what I generally do, are sign errors, and I tend to look for the thing I generally do. And having done this before, I think the last time I did it, I kept a couple extra decimal places. I got 0.862 rounding, so we're definitely where we need to be. One, division right, and I get, for A, I get 17.71. And so now C becomes really nice, because I'm going to scroll up really quick. C has this nice equation here. 0.05 plus 0.05A. So C equals 0.05 plus 0.05A. And so our C becomes 0.05 plus 0.05 times 17.71. And we get 0.935. Which I'll round to 0.94. And am I keeping 2 decimal places? Yeah, I'll keep 2 decimal places on everything. And so our carrying capacity, our population model, now has, we put C upstairs, 1 plus A times e to the negative, and where's our b again? 0.86 t. And we've done it. We've matched our data to our model. And we have the ability to count in billions the cell phone use in India. Notice it's approaching 940 million. Right? If t goes off towards infinity, this term becomes 0, and the carrying capacity upstairs tells you what the limit of the population, the economy, and all the things come together can hold. And so it's 0.94 billion, which is 940 million. The rate at which this is growing is defined by this 0.86 t. And we can look at 17.71 kind of as a proportionality function. But this is it. There's everything you've done in one of the more complex models that human beings have. You know how to have the ability to work with it, which is carrying capacity. You can find the factors in an environment by modeling populations. And by modeling the populations, looking at those factors in the environment, you can figure out what the long-term behavior of an environmental population can be. Right? The original example I used for this, sadly enough, um, these tend to be used in growth rate models. And I have a very good one, which I couldn't find at the beginning of the semester. See, I know if you've ever been in my office, I have loads of bookshelves, and I know it's in one of my books. I thought it was in the Cynthia Young College Algebra. It might have been in the loose leaf version of it, not the hardbound version of it, about coyote populations and what the land carrying capacity is for them. But they make, if I graph a logistic curve, I know I drew one by hand, but let me graph one here. In fact, I'll graph this. Divided by, what do we get? 17.771. So E. Let me switch over to the graph here now that I could type properly. These are what logistical curves end up looking like. And I hope you can appreciate this kind of looks like a upward exponential. This kind of looks like an inverted downward exponential. They really are built off those. But notice, as time goes on, it hits a limit. It hits an asymptote. It hits a value that it comes across. And these actually happen a lot in systems. Being a scientist, we call them equilibrium systems, where the things producing what you want start equaling out the things getting rid of what you want. In chemistry, you can do titration curves, where you look at the point that an equilibrium reaction tips over, and they have what's called a tipping point. Notice this is curving up until right in the middle it starts curving down. The shape of the curve turns, and that spot where it changes over, that point of inflection, is called a tipping point, because in this phase of the curve, the system is pushing to create more cell phone usage. In the latter part of it's actually the things keeping people from using more cell phones take over. And from marketers, I know a marketer who studies the effects of marketing and the creation and uptake of certain products from a marketing standpoint or from a business standpoint. Understanding what causes your points of inflection can help you mitigate those factors. Right? You always, if you're selling, you want to be on the upward side of this, right? If you're cost controlling, you want to be on the downward side of this. And so if you can see where those tipping points are, you can focus on trying to move them. Because as you move them, you can bring down the overall. This is the same thing. The book actually has an example of the H1N1 flu and it matching a logistic curve, and how if you control where the tipping point is, you can control what tends to be your overall rate of infection. And so these models work really, really well for what a population can do overall and what a population can absorb overall, given limiting environmental factors. Now, I'm being very generic with population and trying to give you specific examples, but that population can be money, buying a product, as if this cell phone example, which is why I wanted to use this example, because we tend to always be taught about it in environmental species and predator and prey. Alright, so we used a system of equations to get a logistic curve. That was nice. Why do we choose a logistic curve model? I'm going to use my graph right now to kind of help out. I'm going to put a decay and growth model up. So let's put a growth model on a similar scale. So there is a growth model. And I will say I start with, what did we start with on that? We started with 0.05. And so there is a growth model of an exponential growth. It actually has the same growth factor as the decay factor in here. And notice, for the first part of the curve, up until 2 years in, these models are matching fairly well. This looks exponential. But it shoots off towards infinity. In fact, right about here, right, that's more cell phones than India's population. That is a probable thing, right? There are products that have multiple versions for a person. You can talk in the U.S. it was average televisions per household used to be less than one. Now it's more than one because the idea of owning multiple televisions is acceptable. It's not a huge box in the corner of the room. It's a piece of furniture. And if we look at a decay model, I'll take the same thing with a decay model and we can see why we didn't. But I'm going to use the same rate. And I'm going to start my decay. Where does it appear to start decaying? Around 0.6. Yeah, that's close. I guess I could, let me turn this off for a second and look where these two meet. They meet back here. Right around here, I would say it starts its decay. So I'll put my decay model around there, around 0.2. And so if it starts decaying here, it decays too fastly, right? So when we looked at our data has a general uptick in the data chart, but we know it can't keep growing forever. And if we looked at the numbers, let me come back here. I'm going to do a little flip back and forth between this graph and the blackboard. Apologize for the flipping. This is the thing I miss, is being able to point to 2 different things or 3 different things in a room. If we look at this data, where'd my pointer go? If we look at this data for each year, we notice that between the 4th, 5th, and 6th year, it's not growing as fast as it did in the first 3 years. There's a slowing down to the growth. It only grew by 0.1 in the last year of the data, while the year before that it grew by 0.15. And the key of an exponential growth is it's growing faster each year. The leaps are faster and faster. So this data wouldn't match an exponential. And we see that, hey, it starts looking exponential, and it cuts off. Now, some people will do an exponential, and then they'll say, this is your new total, and you do a decay model afterwards. And that's kind of what the logistic curve does, but in a way, it's an addition and subtraction of these two curves. You can think of the growth having subtracted from it the decay, and you get this curve in the middle that comes out. The subtraction of them subtracts them out. All right. Look at the rules. They're good rules. They're in the book. Get down a little bit. No, stay up. I knew that. Does this work? Let's see if this works. No, maybe. This is it. This is everything I wanted to cover. We ended at the right place. The last example used everything we have done. from a quadratic equation, which is roots of a polynomial, substitution, using a u-value to substitute it in, using logarithms to pull things out of the variables, and all coming from a logistic model, which is one of the models that we have that we need to use here. So at this point, everything is up on Pearson. Not how I wanted to do that. I tried my best to get the technology to point things out for you guys. Sorry about a couple technical hiccups in all of it, but we conveyed information. Please email me questions. I can do individual examples, and I'll post them up to the playlist so that you can look through. But if you need anything, email me. All right. It's been a pleasure. I miss jumping up and down in front of the classroom at you. Hope to see you all soon if possible. If you're going on to different places or whatnot, good luck. Talk to you soon. Be well.